Hey, Calc BC, today we are going to learn 5.3, evaluating improper integrals. This is our third lesson in Unit 5. And as a reminder, this whole unit is advanced integration techniques for BC only. And we are coming from Units 6 and 8 of the College Board's description for our course. If I scroll down here, you can see we've got 4 purple lessons for BC only that we're going to be covering. We already covered integration by parts and partial fractions. This is called evaluating improper integrals. And then next time we'll finish up with arc length, which again, we've already seen in parametric coordinates, and we're going to come back and hit on that in just regular rectangular coordinates as well. So for improper integrals, to dig a little deeper here, an improper integral is an integral that has one or both limits infinite, or has an integrand that is unbounded in the interval of integration. So there's two different ways that an integral could be classified as improper. We're going to look a little bit deeper into what each of those things means today. And improper integrals can be determined using limits of definite integrals. So limits are coming back. Infinity is going to be present in our integrals. So let me pause this and we'll switch over to the notes. All right, so we are going to start off here with the function 1 over x squared. And the first question for us to ponder is, how do you think you would find the following improper integral? From 1 to infinity, f of x dx, with f of x being 1 over x squared. So in other words, we could rewrite this with f of x plugged in, 1 to infinity, 1 over x squared dx. And one visual aid to kind of help us visualize this is over here on the right. So we can imagine that this curve up here is 1 over x squared. Let's say that this a is our 1, and we're going to be going all the way along the x-axis to infinity. As we saw in College Board's course description, an infinity as one of the bounds on our integral is one way that an integral can be determined to be improper. And what I would like us to do here is just kind of solve this as if we were just solving it normally, kind of ignoring the fact that there's an infinity right there and just see what happens. So let's try this. So the first thing I'm going to do is just kind of rewrite this again as x to the negative 2. And that way I know that I can actually integrate x to the negative 2 as negative x to the negative 1. And that needs to be evaluated from 1 to infinity. And so that's what I'm going to do. So I'm going to do negative infinity to the negative 1 minus negative 1 to the negative 1. And that just becomes plus. And so we have, if I rewrite this, I have negative 1 over infinity plus 1 over 1, right? Because that 1 flips to the denominator, the infinity flips to the denominator. And 1 over infinity, right, as a limit that approaches 0. So 1 over infinity for our purposes is really just 0. So we have negative 0 plus 1 or 1. Okay? So even though we had an infinity as a bound on our integral, we evaluated a 1. But my question to you is, logically or thinking about this, looking at this graph, how is it possible that an area that extends towards, infinity in the positive x direction, how is it feasible that that area can add to a total, square units of just 1? It goes on forever, right? And so to kind of think this through a little bit, I have some notes on a separate piece of paper that I'm going to show. It's up to you whether you want to write this down or not, or just kind of follow along. But the truth is that this really does add to 1. The area extends forever, but it's only ever going to add up to 1. So here's what I would like us to take a look at briefly here. We're going to compare two different sums. And this is actually a little bit of a preview for when we get to sequences and series in our next unit. But I would just want us to understand kind of the background of some of these. So take a look. We are going to compare these two sums. So the first one is 1/2 plus 1/3 plus 1/4 plus 1/5 plus 1/6 plus 1/7. And hopefully you can see that the pattern here is that the denominator is increasing by 1 every time. And then we have sum 2. 1/2 plus 1/4 plus 1/8 plus 1/16 plus 1/32, etc. And you can see, hopefully, that the pattern this time is that the denominator is doubling every time. And there is, believe it or not, a big difference between these two sums, even though initially it just seems like, well, they just have a different pattern for their denominator, but they're both both of the fractions are getting smaller and smaller over time. Is it really a big difference? So let's check it out. So for sum 1, I'm going to kind of try to figure out what the first couple terms add up to on our number line here. So the first term we know is 1/2, so that would get us to here. And then we have 1/3, and this is going to be approximate. I'm just kind of guessing. So I'm going to think 1/3 is probably like this length. That's probably about 1/3. And then we get 1/4, which is going to take us to, I don't know, right around here. And then we get 1/5, probably right around here. And then we get 1/6. And you can see I already got past 1.5. I'm just going to kind of keep growing and growing over time, even though I'm growing at a slower rate, right? Because the fractions are getting smaller. So I'm going to be adding a smaller amount every time, but I'm going to continue to grow. Take a look at sum 2. 1/2 is where we start. So we're starting right around here. And then I'm going to add 1/4. And then I'm going to add 1/8. And then I'm going to add 1/16. And every time I'm getting halfway closer to 1. So I added 1/2. The distance between 1/2 and 1 is 1/2. And I added 1/4 next, so I got halfway to 1. Then I added 1/8, so I got halfway to 1. Now I'm adding 1/16, so I'm getting halfway to 1. And the pattern is going to continue. Every time I'm going to get closer and closer to 1, but I'm only going to be going halfway there. So this sum of fractions goes on forever, but the limit of what this sum approaches is 1. So even though this is an infinite amount of numbers summed together, they add up to 1. And that's exactly what's happening in our improper integral over here. This is an infinite area, but it adds up to 1. And because it's an area, I wanted to also show it to you visually as an area. So I want to think now as if this square, and I realize my squares aren't exactly even, but think of these two as squares, and they're going to total 1 square unit, okay? So for my first sum, I started with 1/2. So I'm going to fill in 1/2 because that's going to be an area of 1/2. And then the next number was 1/3. So, gosh, I got to try to figure out what's 1/3 of what's left. Sorry, 1/3 of a whole unit. That's going to take us to probably like right around here. And now I'm at my third number, 1/4. And I'm already going to be kind of overflowing this 1 square unit, right? And no matter how big my area started out as, if I added numbers, eventually this is not going to like slow down enough where it has a limit. This is going to keep growing and growing forever, even though it grows much slower after a long time. It just keeps growing. So this is going to like overflow. No matter how big this initial box was, it's always going to overflow. All right, what about sum number 2? Think about this again as being 1 square unit. It's a 1 by 1 square. And so we're going to start by adding an area of 1/2. And then I'm going to add 1/4. Then I'm going to add 1/8. Then I'm going to add 1/16. and I'm going to add a 32nd. And you can tell I can keep going. I'm going to keep being able to add fractions forever because they keep taking up half of the remaining space. So, the limit of all of these fractions added together perfectly fits inside this 1 by 1 square, or it would equal 1, right? 1 square unit. And this is demonstrating the difference between what we call convergence and divergence. And this is going to be terms that we need to know in our notes today. So convergence is when an infinite sum, has a limit of a certain number. So a convergence was the purple one here. I don't know if you can actually tell that I was using purple. I think you can. Convergence is when the sum adds to a finite real number. While divergence, which was the red one up here, is when a sum does not have a bound and it therefore approaches infinity. And again, even though we're talking about like adding fractions together, it still applies to the idea of an integral area as well, as we are looking at in our notes today. So that's a little bit of a preview. We've got two types of sequences that we can add together. Convergence versus divergence is the point, okay? So in this first example here that we just kind of looked through, since we found an answer of 1, we would say that this integral converges to 1. Because it has an actual, finite sum that we found, and it is 1. So even though this area extends forever in the positive x direction, we can say that if we could take this area and kind of pour it two-dimensionally into a 1 by 1 square, it's never going to overflow. Even though you'll be able to add to it forever, it's always approaching a limit of 1 unit. So that is what we say the integral evaluates to. It evaluates to 1. So let's start to fill in some definitions here. And if you're writing this on separate paper, you do not necessarily have to write every single word. It's up to you how you want to summarize this. I just expect you to at least have enough that you know what's going on, okay? All right, so the definition of a definite integral from a to b f of x dx requires that the interval a to b inclusive be finite. And also requires that f of x be continuous on the interval from a to b, right? So that's just kind of telling us the basics of original integrals that you learned in AB, right? The interval must be finite from a to b. You've never seen infinity as a bound before. And the curve must be continuous within the interval, or else, you can't take the integral. Because of these requirements, if one or both of the limits of integration are infinite, or if f of x has an infinite discontinuity, in the interval, then a to b f of x dx is called an improper integral. All right, so what is this saying? What are these two things? The first one said that if one or both of the limits of integration are infinite. So that's kind of like this example up here. So that would be like if we had a curve like this and we were evaluating it to infinity. That would cause an improper integral. The other option, if we have an infinite discontinuity in the interval, what is that talking about? That's saying, like, let's say we're looking at a curve that goes like this. And we're only evaluating from A to B, but somewhere in there, we've got something like a vertical asymptote. So that would be an infinite discontinuity. So again, that's causing an improper integral because now our area is kind of screwed over by the fact that, right in the middle, we got infinity going on, right? So those are the two possible ways that we have an improper integral. So f of x has an infinite discontinuity at c if the limit from the right or the left is infinity or negative infinity. And that's exactly what I just drew. Let's say that this x value right here is c. If the limit from the left or from the right is infinity, we've got an infinite discontinuity. It could also have been negative infinity, all right? So let's keep going. Case 1. If f is continuous on the interval starting at a, going to infinity, we might have an integral from a to infinity of f of x. And this is where notation is important. We're going to rewrite this using limit notation. So these three cases, let me back up for a second. These three cases are going to tell us exactly how we have to rewrite our integrals in order to evaluate properly. All the way back up here at the top, this actually is not correct notation. So even though we got the answer of 1, this would have been a major problem if you did something like this on a test. So I'm going to write up here, major problem, change before you evaluate using limits. And that's what we're going to do starting down here. So these three cases are going to tell us how we have to change the way that we write this so that we can actually solve without kind of breaking the rules of integration. So if we're going from a to infinity, we are going to have to rewrite this as the limit as b approaches infinity of a to b f of x dx. If we're going from negative infinity to b, we've got to rewrite this as the limit from a, as a approaches negative infinity, integral from a to b of f of x dx. And if f is continuous on the interval, but there's some c in the middle where we had an infinite discontinuity, then we've got to rewrite this in two pieces. So we have, let's see. Well, first we would split this. Oh, I'm sorry. Let me back up. I kind of lost track of what we're talking about here. The endpoints are negative infinity and infinity in this one. We're going to come back to the idea of an infinite discontinuity later. So this is specific to the idea of limits of integration are infinite. I'm going to write that up here. So let's say the limits of integration are infinite. That's what these three cases are for. So we have to split this up into two different integrals. We cannot evaluate from negative infinity to infinity at once. So we would write this as from negative infinity to something else, maybe c. And then the other end from c to infinity. And then we would have to split it up using what we already said. So we're going to have to rewrite this as the limit as a approaches negative infinity from a to c plus the limit as b approaches positive infinity from c to b. And c is going to be some constant in between. So we can pick what c is. It's pretty common to pick 0. We just have to split it into, we can't evaluate the entire limit at once, okay? It'll make sense what that means once we do some practice problems. But anyway, the integral from a to infinity or the integral from negative infinity to b converge if the limit is finite. They diverge if the limit is infinite or does not exist. The case 3, negative infinity to infinity. So if we're finding the entire domain integral, it diverges if either the negative infinity to some c that we pick, normally 0, or the integral from c to infinity diverge. So even if one of those diverges and the other one doesn't, overall, the final integral is going to diverge. That just kind of makes up for, like, if we look for the positive end and the negative end, and one of them adds to a nice number like 1 did up at the top, and the other one is going to grow forever, like the other case from our example. Overall, if one of them stops growing but the other one keeps growing, it makes sense that overall it's going to keep growing, right? So it really would be diverging and would approach infinity overall. But anyway, we'll come back to that when we get there. Let's take a look at some examples. Example 1, an improper integral that diverges. Okay, so we're going to start with the integral from 1 to infinity, 1 over x dx. So we've got to check, is 1 over x continuous on this interval from 1 to infinity? And the answer is yes. 1 over x is a problem when x equals 0, but everywhere else it's continuous. So we're going to have to make note of this every time. So that's why this is on here. We're going to note that the function is continuous on the interval from 1 to infinity. So we are allowed to proceed. This is something that I would want you to write. If you were given an improper integral, you would want to check that the function itself was actually continuous and didn't have a vertical asymptote halfway through or something. So let's start this. The first step is always going to be to take the given problem and rewrite it using limits so that we have proper notation. We just kind of switch it from an improper integral to a regular proper integral with a limit in front. So we're going to make this the limit as b approaches infinity, integral from 1 to b of 1 over x dx, okay? So the only reason I'm using b here is that it's most common for an integral to see it start as from a to b. So since, you know, the upper bound of the integral is what we are replacing, that's why I used b. I recommend that you do the same. It just makes things easier if you keep track of a and then b, and then that's all you have to do. We don't want to use x because we already used x in this equation, right? In this expression. We don't want to use x again. So now we want to start to solve it. So this is 1 over x. So the integral is going to be the natural log of the absolute value of x. We still have to write this limit statement every single time. So it's going to be the natural log of the absolute value of x evaluated from 1 to b, right? You can see this is just a normal way of doing an integral. So then we are going to start to evaluate. Whenever the b comes into play, I'm going to rewrite the limit in front of it. So it becomes the natural log of b minus the natural log of 1. So I'm going to have to write the limit in front. So it's the limit as b approaches infinity of the natural log of b, absolute value, minus the natural log of 1. And so now I'm going to think about, okay, so what is the natural log of b as b approaches infinity? So I'm going to have to think about what that graph looks like. So let me get my calculator just so that I can make sure I remember. All right, so I got my calculator. I'm going to just real quickly graph natural log of x just so I can examine it. The curve grows slower over time, but you know, if you think of this through a little bit, there is no reason that there's any horizontal asymptote that this curve is approaching. So as we approach infinity along the x-axis here, which is our b's, the y value just keeps going up. So this limit approaches infinity. We would not want to replace this with a statement that had infinity plugged in. That is kind of returning to the idea of an improper state, right? You don't usually see infinities just hanging out in expressions. So, but it is okay to say that this approaches infinity, therefore this whole thing diverges. And when an integral diverges, we just write diverges, and as long as we showed the work, that's the answer. When we converge, we usually converge to a specific number, right? Because there is a sum. If it diverges, it means it's approaching infinity. You could say something like it diverges to infinity, but all we really need to write to answer the question is that it diverges, and that's the end, okay? What about if an improper integral does converge? Let's check this next one. So we have an integral from 0 to infinity of e to the negative x dx. Note that this function is continuous, and we could check that on the graph. So we don't have to worry about breaking it up. We'll see some examples of that later. So let's try this. First step, as always with improper integrals, is to rewrite using limits so that we don't have infinity in our actual expression. So we're going to have the limit once again as b approaches infinity. We're going to go 0 to b e to the negative x dx. Once again, the infinity was our upper bound, so that's why I'm using b. And let's see. So one of the easiest things to mess up when you're doing this work is to not write the limit statement every time, but we need to. So I'm going to write limit as b approaches infinity. And if I take the integral of e to the negative x, I'm going to get negative e to the negative x. I'm going to have to evaluate that from 0 to b. And then I'm going to plug in the b and the 0. So the first one has the b in it. So I'm going to write the limit as b approaches infinity of negative e to the negative b minus negative e to the negative 0, or just 0. All right, so let's keep going then. Negative e to the negative b. Well, negative b means I could flip this. So this is now going to be the limit as b approaches infinity of, what did we say? Negative 1 over e to the b. And then e to the 0 is just 1, right? Anything to the 0 power is 1. So this is going to be plus 1. And so now I think about, okay, what happens as I plug in infinity here into this exponent? It's making the denominator grow infinitely. So that means that we really have 1 over infinity. Now, again, I'm not going to write 1 over infinity in my work, right? Because that kind of returns to an improper statement. All I'm going to do is say, okay, this limit approaches 0. So I'm going to actually just evaluate it and write 0 plus 1 equals 1. So we found an answer. So we would say that this improper integral converges to 1, right? Even though it goes on forever, you add up the whole area and it actually approaches 1. All right, let's try another one. Another improper integral that converges. The integral from 0 to infinity of 1 over x squared plus 1 dx. This function is continuous from 0 to infinity. Again, you could check that out on the graph to make sure. All right. And so let's immediately, as always, we're going to immediately change to a limit. Once again, it's the upper bound, so we're going to use b. The limit as b approaches infinity, integral from 0 to b of 1 over x squared plus 1 dx. And I am going to remember that the derivative of arctan is 1 over x squared plus 1. I think we saw that recently, so that should be fresh in your mind, but you can look that up if you need to. So I know that this is now going to be the limit as b approaches infinity of arctan, or tan to the negative 1 of x, evaluated from 0 to b. And so I can start to plug this in. So we have the limit as b approaches infinity of the arctan of b minus the arctan of 0. And it really is going to be helpful if we think about what the graph of arctan looks like. You can sketch this on your paper. I encourage you to. And if you do, you will remember that we actually have two horizontal asymptotes at pi over 2 and negative pi over 2. And the graph, which I'll make in a different color here, goes like this. With those horizontal asymptotes. Okay, so let's think about what's going to happen when we plug in for these limits. So the limit as b approaches infinity in arctan of b. So as the x gets larger and larger, what is the y value approaching? And the answer is that it's approaching pi over 2 because that's our horizontal asymptote. So this actually equals pi over 2. The arctan of 0, you can see right here, if I plug in 0 for x, I get 0 for y. There's a point there at 0, 0. So we get pi over 2. Or you could write that this converges to pi over 2. Okay, let's keep going. Example 3, using L'Hopital's rule with an improper integral. The integral from 1 to infinity of 1 minus x times e to the negative x dx. This function, once again, is continuous, and we should check that before we get started. I don't think there's anything from any number from 1 to infinity that I could plug in here that would cause a problem. Yeah, it works. Even if I plug in 1, I get 0 times something, so it's 0, but that's not a problem. That would only be if we were dividing by 0. So that's okay. So let's get started. So integral from 1 to infinity. As always, we're going to start off by switching to the limit notation. So we're going to have the limit as b approaches infinity of the integral from 1 to b, 1 minus x, e to the negative x dx. And we are going to start off by using IBP, which stands for integration by parts. So if we do that, what we will find is that our u is going to be the 1 minus x. Our du is going to be negative 1 dx. Our dv is going to be what? E to the negative x dx. And our v is going to be negative e to the negative x. Okay. So I'm going to rewrite this using ultraviolet voodoo, uv minus the integral of v du. So we're going to have, well, first of all, I should rewrite this limit first. So it's going to be the limit as b approaches infinity of the whole thing. And it's going to be u times v, so 1 minus x times v, negative e to the negative x, minus the integral of v, negative e to the negative x times du. So negative 1 dx. And that whole thing needs to be evaluated from 1 to b. And there we go. Okay. So let's think through what we should do next. Can we actually evaluate this integral this time? I think we can. I'm going to rewrite this once, I think, just to kind of clear up these negatives. Well, I suppose I could just say right now, we have a negative times a negative in here, so that's going to become positive. That negative is extra, so it'll just stay minus. Okay, so we can do this. We get limit as b approaches infinity of 1 minus x times negative e to the negative x. And if we integrate e to the negative x, we're going to get negative e to the negative x. So then we have a negative times a negative. So it's going to be plus e to the negative x. And that is still needing to be evaluated from 1 to b. Okay. So now we can go one step further. We can actually start to plug in b and plug in 1. So we're going to, for the first part, we'll still have the limit And we'll have 1 minus b times negative e to the negative b plus e to the negative b minus plugging in 1 for everything. So we'll have 1 minus 1 times negative e to the negative 1 plus e to the negative 1. And notice that we are now told to use L'Hopital's rule, which we'll get to in a second. So let's see what we can do first. I'm going to split this into 2 separate limits because I think that's going to make it easier for us to see. So we'll have the limit as b approaches infinity of, and since this has a negative in front, in the exponent, I'm going to move it to the denominator. So it's going to be 1 minus b over negative e to the b. This second one is also going to need to have that limit in front. And we can rewrite it as 1 over e to the b. And then we have, let's see what's going on over here. This is all equal to 0. And then we have this as 1 over e. So it's going to be minus 0 plus 1 over e. Okay. Oh, we're getting there. We're getting there. We're getting there. Okay. So this second limit isn't too bad, right? 1 over something that as the b increases forever, this is going to approach infinity. So we have 1 over infinity, which is 0. So we've got something plus 0 minus 1 over e, right? This 1 over e has this negative from here. So we're going to use L'Hopital's rule to evaluate the first limit. So let's check this. The limit of the numerator, we've got to check to make sure the limit of the numerator and the limit of the denominator are both some form of infinity. So let's check that. If we check the limit as b approaches infinity of the numerator, 1 minus b, well, 1 minus infinity, that's going to pretty much simplify to negative infinity. And for the bottom, we have the limit as b approaches infinity of negative e to the b. That's going to also approach negative infinity. So therefore, if you haven't seen that before, the 3 dots means therefore. That means therefore L'Hopital's rule applies. And we know that means that we can take the derivative of the numerator and the derivative of the denominator, and the limit will be the same. So let's try that. Therefore, we can say that the limit as b approaches infinity is the same as the derivative of 1 minus b, which is going to be negative 1, the derivative of negative e to the b, which is still negative e to the b. And now, if I think about plugging in infinity, it is very similar to this one up here, right? Because we have a negative over negative. That just equals 0. So this is now equal to 0 plus 0 minus 1 over e, or just negative 1 over e. So after all that, we got an answer that's actually not infinity. So this converges to negative 1 over e. All right, I'm going to purposely be showing you some more complicated improper integrals like this throughout the notes. Yes, it might be a little much for me to expect you to do this right, like initially, because you've never seen something like this before. But the more that we see some of these properties or other rules that we've learned previously applied in integrals like this, the easier it'll be for you to spot it when we have to do it, out in the wild, when we don't know for sure, we're not given these hints, right? That this is what we're supposed to do. So we're going to try some more. Okay, so let's take a look at example 4. Infinite upper and lower limits of integration. So this is that case 3 from the first page, where we have an integral that goes from negative infinity all the way to positive infinity. So the first thing we need to do is check to make sure that this function is continuous, and it is. It doesn't matter what number I plug in for x, this is always going to be continuous. So it is continuous for the whole interval of the integral, negative infinity to infinity. So the first thing that I'm going to do is split this up and include the limit statements. Let me make sure this is perfectly focused. Oh my gosh, that's not focused. There we go. Okay. So as I was saying before, we can't just all at once make this limit statement, go from A to B with a limit for A and a limit for B all in one. We got to split this into two and check both. So what I'm going to do, first step, is split this up into the integral from negative infinity to 0. And then the integral from 0 to positive infinity. And we know from properties of integrals that that is going to sum to the same thing, right? We just split it in two, should work out okay. Okay? But hopefully you're noticing, wait a second, we can't have infinity in our integrals. These are still improper integrals, and that is correct. So the next thing we have to do is write the limits. So for this first one, now we actually have a negative infinity as our lower bound. So we are going to change that to an a. And we're going to say as a approaches negative infinity, integral from a to 0. And for the second one, we're also going to make another limit. And this one is going to be as b approaches positive infinity, integral from 0 to b, e to the x over 1 plus e to the 2x dx. Okay, so we got rid of the improperness. So now we're allowed to solve. So that's what we're going to do. And to make this a little nicer, we are going to use u substitution. So I'm going to let u equal e to the x, which means that du equals e to the x dx. And let's see, how am I going to put this in here? The reason I want to do that is because now e to the x shows up in the denominator. Here, I'll rewrite these so that you can see what I'm talking about. Before we actually plug in the u, I'm going to rewrite each one of these so you can see how I'm going to replace this and the strategy here. So for the first one, we have the limit as a approaches negative infinity, integral from a to 0. I'm going to separate this as 1 over 1 plus e to the x squared times e to the x dx. So you can see I just pulled the e to the x from the numerator to the side and still multiplied it. And I changed e to the 2x to e to the x squared, right? Because x times 2 is 2x, so that we're allowed to do that. So I'm going to do that exact same thing for the second integral. And now you can see where this is going, hopefully. Now we are ready for the u substitution. So we're going to have limit as a approaches negative infinity, integral from a to 0, and we'll have 1 over 1 plus u squared, and the e to the x dx just turns into du. Don't forget to write limit every single time. Okay, so that turned into the perfect integral to represent arctan, right? This is now, with the u substitution applied, this is now the derivative of arctan. So we can replace both of these. So I'm going to write the limit as a approaches negative infinity from a to 0 of tangent inverse of u. Oh, geez. I made a very silly mistake. I still wrote the integral. Hold on, I gotta grab my whiteout real quick. Okay, let me wipe that out. I don't want to have to scribble that out, make it not neat. Okay. So once we evaluate, we don't write the integral, obviously. So this is now the limit as a approaches negative infinity of tangent negative 1 of u evaluated Hold on. All right, I'm mad at myself, and you might be yelling at your screen this whole time, so I'm very sorry about that. I have always told you that when you use substitution, you want to change your limits of integration or the bounds of your integration immediately, and that way you don't have to go back to x's. And then I broke my own rule, so I'm going to backtrack for a second. I already whited out the bounds. Sorry about that. Let's get back up to speed. So we were going from a to 0. U now equals e to the x. So this is going to be e to the a and e to the 0. And same thing over here, we're going to have e to the 0 and e to the b. And now once I actually evaluate the integral or take the integral, my bounds have to change. So this is from e to the a. E to the 0 just means 1. So I can just change that to 1. And this one's going to be from 1 to e to the b. All right. Whew. Now we're back on track. Sorry about that. So let's keep going so we can actually start to evaluate this. And so for the first one here, we have the arctan of 1 minus, and this second one has the a in it. So we have to include the limit statement, the limit as a approaches negative infinity of arctan of e to the a. So that whole thing just came from here. Now I'm going to do the same thing for the second one. So it's plus, for this first one, I have the b involved. So I need to write the limit statement as b approaches positive infinity, tangent to the negative 1 of e to the b, minus the second one doesn't have b in it. It's just arctan of 1 again. Okay? So I need to make sure that every single piece of this doesn't equal infinity, or else we're going to have problems. So let's kind of back up a second. We're looking at arctan again. We made a really nice sketch of arctan over here. So the first thing I notice is that I have arctan of 1 minus arctan of 1. Hey, wouldn't it be really nice if that canceled out? It seems like it does. The only thing I want to make sure is that neither of those terms equal infinity, because then we have a problem. And I can tell somewhere along this x-axis is a value of 1. And wherever it is, it doesn't matter. The y is definitely not going to equal infinity. I can tell that just from like a rough glance. So they will successfully be able to cancel out. So this cancels out this. Then we're left with these two limits that approach infinity and negative infinity. So can we evaluate this? The limit as a approaches negative infinity of e to the a. So let's think about what's going to happen. If we plug in negative infinity in for a, well, that's negative. So it's really 1 over e to the infinity, which is going to approach 0. So we've got this arctan of 0 essentially going on here. And if you think about 0 on our graph, we figured out before that the y value was 0. So the arctan of 0, this really just approaches 0. So we've got a negative 0 plus as b approaches infinity. So e to the infinity is going to mean that this internal part here approaches infinity. So the arctan of infinity, we saw before, the y value approaches this horizontal asymptote of pi over 2. So we've got negative 0 plus pi over 2, which is going to sum to pi over 2. So this converges to pi over 2. after all that. All right. So again, sorry about that mix up halfway through that question, but that converges to pi over 2. All right. Next up, we are now going to look at the cases for when we have the infinite discontinuity. So if you think back to the first page, we talked about if the limits of the integration are infinite already. But remember, there was a second case or a second scenario when we have an improper integral, and that's when we have an infinite discontinuity somewhere in the interval. So we're going to refer to this next section as infinite discontinuity. All right, and then again, there's 3 cases. So case 1, if f is continuous on the interval and has an infinite discontinuity at b. So let's say there's an infinite discontinuity or a vertical asymptote at the right edge of our interval from a to b. First of all, that's going to look something like this. If you want to sketch this on the side, from a to b, and it's going to look something like this probably. And if you try to shade it, you'll see it like approaches infinity. Okay, so we're going to rewrite this so that it has the infinity accounted for. So we're going to have to say something like this. The limit as k approaches b from the left of the integral from a to k f of x dx. And that's going to make more sense when we actually have numbers plugged in. But what on earth is going on here? I used a different letter besides A, B, and C because we already talked about that. But we're saying as k approaches b from the left. So we are now accounting for the fact that we can't have an integral from a to b if we're not continuous on the closed interval from a to b with brackets, which we're not. So now we're saying, well, we can say from a to b, except not to b, to k as k approaches b from the left. And you can see we don't care about a b from the right because that's not part of our shaded area. So we're only approaching b from the left. So that's why did I put a 1 there? Oh my gosh, I'm going crazy. K approaches b from the left. That's the proper notation. Once again, my bad. Case 2, if f is continuous from a to b but has an infinite discontinuity at a. So that situation would be kind of the opposite. If we're going from a to b, it would look something like this. So similarly, we're going to say the limit as k approaches a from the right, right? Because now we're only interested in coming from the right. The integral from k to b f of x dx. And then case 3, if f is continuous on the interval a to b, except for some c in the middle, at which f has an infinite discontinuity, then we've got to split into 2 integrals. The scenario would be if we go from a to b, but we have a vertical asymptote somewhere in the middle, like this. And if I shade that, you'll see we have a problem somewhere in the middle at some x value c. So we're going to say that would have to be split to the integral from a to c f of x dx plus the integral from c to b f of x dx, which would then have to be split according to these same rules. So let's do that quickly. So the c is the problem point. So now we have to do a limit as k approaches c from the left, integral from a to k f of x dx, plus the limit as k approaches c from the right, integral from k to b f of x dx. Okay. So we're going to try not to get too bogged down in that notation, but we're going to make sure that we do it correctly as we go. Case 1 and case 2 converge if the limit is defined and able to be found. They diverge if the limit is undefined or infinity or does not exist. Case 3 diverges if either the first part or the second part diverge, just like before. All right, so let's actually apply that on this last page of the notes. Example 6, an improper integral with an infinite discontinuity. We are going to do the integral from 0 to 1 of 1 over the cube root of x dx. Note that the function f of x does have an infinite discontinuity and is at x equals 0, right? We can't plug in 0 here. We get 1 over 0. This would be a vertical asymptote. So we're going to have to set this up using the rules from the previous page. As always, we want to initially start by immediately removing the improperness from this integral and representing that with a limit instead. So we're going to say the limit as k approaches 0 from the right of the integral from k to 1 of 1 over the cube root of x dx. Okay, so just to remind you, k is now representing 0 because 0 was the problem point. The closed interval from 0 to 1 would have to be fully continuous in order for us to actually evaluate that integral in its first form. Well, that's not true. So we're going to say from k to 1 as k approaches 0 from the right so that we can still evaluate in a proper way. So I'm going to rewrite this so that it's a little bit nicer. To evaluate, I'm going to have to rewrite that limit statement every single time. And I'm going to write it as x to the negative 1/3, just so that I can use my integral rules easier. So this is going to become the limit as k approaches 0 from the right of 3/2 x to the 2/3 evaluated from k to 1. And then I can start to plug this in. So when I plug in the 1, I don't have to write the limit. So we have 3/2 times 1 to the 2/3 minus the limit as k approaches 0 from the right of 3/2 k to the 2/3. All right, so let's think about this right here. What happens as we plug in 0? Well, if we straight up plug in 0, we get 0. And sure enough, as we approach that from the right, it's still going to be approaching 0. Let's quickly take a look at that graph just to make sure it makes sense. So if we plug in 3/2 x to the 2/3. Sure enough, as we approach from the right, you can see that curve is approaching a y value of 0. So that worked out. So we have 3/2 times 1 to the 2/3, which is just 1. So we have 3/2 minus this whole thing, which approached 0. So we have 3/2. So sure enough, this converges to 3/2. All right, let's try an improper integral that diverges. Integral from 0 to 2 of 1 over x cubed dx. Note that this function has an infinite discontinuity at x equals 0, just like the previous question. So we're going to have to use the limit as k approaches 0 from the right of the integral from k to 2. And I'm going to just jump to x to the negative 3rd dx so that I can evaluate this a little bit easier. So we have to write the limit statement every single time. This becomes x to the negative 2 times negative 1/2. And that has to be evaluated from k to 2. So the first one's going to be negative 1/2 times 2 to the negative 2 minus the limit as k approaches 0 from the right of -1/2 k to the -2. And so I could evaluate that first part, and it would become 2 to the -2 is 1/4. So we have 1/4 times a half, which is 1/8. So we get -1/8 minus, I'm just going to rewrite this limit statement for a second here so we can kind of examine it. And I'm going to rewrite it as -1/2k squared. So I'm going to move that k to the -2 to the denominator and make it 2 positive. As we approach 0 from the right, well, if we straight up plug in 0, we're going to have an issue because we're dividing by 0. And I'm pretty sure if we approach 0 from the side, the same thing is going to happen. We could look at the graph just to make sure. So let's do that. I'm going to have negative, and then a fraction, 1/2x squared. Take a look at the graph. Yeah, okay, so as we approach 0 from the right side, it's going to equal -infinity because of this negative in front. So yeah, that's going to be a problem. And again, I don't want to just straight up start writing infinity in my equation as part of the expression, because I'm not treating infinity like it's some other variable or some constant. But we do have a problem. This whole thing approaches -infinity. So that is something that I want to write. I want to write that this, how I'm going to do this. That whole thing right there approaches -infinity. So therefore, the whole thing diverges. So it's -1/8, essentially -1/8 minus -infinity. Well, that's going to be a big problem. So that diverges. That area doesn't approach a specific number. It keeps growing forever. We've got 2 more examples to get through. Example 8, an improper integral with an interior discontinuity. This is one of the tricky ones where we're going to have to split it into 2. Just like all these other ones, actually, this is pretty much the same as the previous example. 1/x³ has a discontinuity at x equals 0. That's where we have a vertical asymptote. So we are going to have to split this integral into 2. It's going to go from -1 to 0 of x to the -3rd dx plus the integral from 0 to 2 of x to the -3rd dx. And I'm going to immediately rewrite that using the limit statements. So the first one is going to be the limit as k approaches 0 from the left of -1 to k. The second one has a problem at 0, and that's the left bound, so we're going to have to approach it from the right. K to 2, x to the -3rd dx. And I could keep going, but you know what? Actually, I do want to show you something about that, so I'm going to keep going. You can already tell the final answer is going to be that this diverges because the second part is the integral from the previous question. And since this integral, we already know diverges, the whole thing is going to diverge, even if this part happened to work out. Since the second part diverges, the whole thing diverges. But let me just show you something about this. So we are going to keep going. So let's see, we've got the limit as k approaches 0 from the left of -1/2 x to the -2 evaluated from -1 to k plus the limit as k approaches 0 from the right of -1/2 x to the -2 evaluated from k to 2. And if we wrote all of that out, what will be fine? Let's do that quickly. So we got the limit as k approaches 0 from the left of -1/2 k to the -2 minus -1/2 times -1 to the -2 plus -1/2 times 2 to the -2 minus the limit as k approaches 0 from the right of -1/2 k to the -2. All right. So something that is potentially tempting when you're solving a question like this is to say, wait a minute, we've got two very similar limits. One is added and one is subtracted. So let's cancel them out. But we don't want to do that. We don't want to cancel out infinities when one of them was part of the first integral and one of them was part of the second integral. We want to think of these still in their separate forms. And since this one is going to not work and this one is also going to not work, overall, the whole thing doesn't work. So this diverges because each part of it approached some form of infinity. Okay? Example 9, a doubly improper integral. Okay? This one is pretty complicated. And doubly improper is going to mean that we have a vertical asymptote and a horizontal asymptote that we're working with here. And both of them are going to cause us to be improper. We're going to have a limit of a limit. So get ready. So first off, we have an infinite discontinuity in this fraction when x equals 0. If you plug in 0, you're going to get 1 over 0, which is going to cause us to be undefined. And that is in infinite discontinuity. It's a vertical asymptote. We also have an infinity as one of the bounds of our integral. So we've got a lot of different problems here. So here's what we're going to do. The upper bound is going to have to be replaced by b, but the lower bound is also going to have to be replaced because that's where our other discontinuity is. So the lower bound is kind of the most recent kind of question that we were talking about. So that's going to be replaced by the limit as k approaches 0 from the right. And that's because if you think we're going from 0 to infinity, the 0 had a vertical asymptote, so we're going to be approaching 0 from the right, because that's the part that's actually part of our shaded area. And so that's going to be replaced by k, but we also need to replace that infinity. So we're also going to have a double limit. It's going to be the limit as b approaches infinity. So now our integral is from k to b. And so we have 1 over the square root of x times x plus 1 dx. I am going to say that we should let u equal the square root of x. Or x to the 1/2. Du, therefore, could equal 1/2 x to the negative 1/2 times dx. And that's going to be pretty nice because, let's see, why is that going to be so nice? Well, this, I'm going to rewrite this one so that we can see, just like we did with that other question. So we're going to have to write both of these limits every time. From k to b. And let's see. I'm going to rewrite this first part as 1 over x plus 1. And then 1 over the square root of x, I could rewrite as x to the negative 1/2. So now we can see, okay, this is going to look pretty similar to my du. The only thing I'm going to change here is that I have to have a 1/2. So I'm going to plop a 1/2 in there and then pull a 2 out in front. I guess I could stick it right here. And then we are good to go. So let's try this. So now we're going to have the limit as k approaches 0 from the right, the limit as b approaches infinity. I'm going to come back to the bounds. But 1 over x plus 1, since u was square root of x, we could replace that with u squared. So it's going to become 1 over u squared plus 1, right? Because u squared is going to equal x. And then this whole thing just changes to du. I'm not going to forget this time. I have to change the bounds of my integral based off of my u substitution. So it's going to be the square root of k and the square root of b. Okay, so next step, 1 over u squared plus 1. Oh my gosh, wait a second, I forgot about my 2. Let me make sure I include that 2 in here. That 2 didn't go away. So 1 over u squared plus 1 is, I believe, once again, arctan. So this can now become the limit as k approaches 0 from the right and the limit as b approaches infinity of 2 tangent inverse of u evaluated from the square root of k to the square root of b. Okay. And now let's try to do that. So we're going to have the limit, the upper one is b, so it's going to be the limit as b approaches infinity of 2 arctan of the square root of b minus the limit as k approaches 0 from the right of 2 arctan of the square root of k. Okay, so let's see if we can actually evaluate these. So this first one, limit as b approaches infinity of 2 times arctan of the square root of b. So I'm going to just kind of ignore that 2 for a second. I'll put it back in at the end. As b approaches infinity. So the square root of infinity, it's still going to be approaching infinity. So we already know from our previous diagram, right? If we go back to that, as x approaches infinity, the y value of arctan approaches pi over 2. That's the horizontal asymptote there. So we can replace this with pi over 2. And over here, as we approach 0 from the right, square rooting from 0 from the right is still going to be positive values coming from the right. And that's going to equal 0. We've seen that before. Okay, so we really just have 2 times pi over 2 minus 0, or pi. So this converges to pi after all that, which is really crazy, right? I want to show you that graph real quick. I'm going to pause so you don't have to watch me type it in, but give me 1 second. All right, so you can see I typed in this original equation, and if we take a look at the graph, you can see that from 0 to infinity is what's going to be shaded, and we have a vertical asymptote here at the y-axis, and we have a horizontal asymptote on the x-axis. So that's causing this what we call doubly improper situation, where we had to kind of adjust both bounds of our integral in order to be able to properly process this. And it's kind of crazy that even though we have 2 different versions of infinity playing into our area, if we could take this whole area and kind of stack it or crunch it together, it would never get larger than an area of pi square units, which is just crazy, but it's true. And we can now do integrals like this, all right? So that is it. Thank you very much for watching. Don't forget to submit your notes and have a great day.